Imagine a world without the protective embrace of Earth's magnetic field. Without this invisible shield, our planet would be exposed to the full fury of the sun's radiation. The consequences would be catastrophic, altering the very fabric of life as we know it. Deadly radiation from the sun would bombard our planet, stripping away our atmosphere and leaving the surface barren and lifeless. The intense solar winds would erode the atmosphere, making it impossible for life to sustain. Our oceans would evaporate and the surface would become a desolate wasteland, much like Mars. Thankfully, our planet is not defenseless. Encircling Earth like invisible guardians lie the Van Allen radiation belts. These belts are crucial in maintaining the delicate balance that allows life to thrive on our planet. Two donut-shaped regions of trapped charged particles act as a shield against the sun's relentless radiation. These belts capture and deflect the harmful solar particles, preventing them from reaching the Earth's surface. They are a dynamic and complex system, constantly changing in response to the sun's activity. These belts, named after their discoverer James Van Allen, are a testament to the power and beauty of our universe. Van Allen's pioneering work in the 1950s led to the discovery of these radiation belts, revolutionizing our understanding of space weather and its impact on Earth. They are a dynamic and complex system, constantly changing in response to the sun's activity. Solar storms and flares can cause the belts to swell and intensify, posing challenges for satellites and space missions. Understanding these changes is crucial for predicting space weather and protecting our technological infrastructure. Their existence is a crucial reminder of the delicate balance that makes life on Earth possible. Without the Van Allen belts, our planet would be a vastly different place, inhospitable to life as we know it. They are a vital component of Earth's natural defense system. The Van Allen belts are not merely a scientific curiosity. They are a key area of study for scientists and researchers who seek to understand the complexities of space weather and its effects on our planet. By studying these belts, we gain insights into the broader workings of our solar system. They have profound implications for our technological civilization. Satellites, essential for communication, navigation, and scientific observation, orbit within or even pass through these belts. The radiation within the belts can damage satellite electronics and affect their operation. Satellites, essential for communication, navigation, and scientific observation, orbit within or even pass through these belts. Engineers must design satellites to withstand the harsh conditions within the belts, ensuring they can continue to function and provide critical services. Understanding the belt's behavior is critical for protecting these valuable assets from the damaging effects of radiation. Space agencies and researchers continuously monitor the belts, developing strategies to mitigate the risks posed by space weather. The study of the Van Allen belts is a journey into the heart of space weather. It involves a multidisciplinary approach, combining physics, engineering, and space science to unravel the mysteries of these radiation belts and their interactions with the Sun and Earth. It is a field that is both fascinating and essential, holding the key to safeguarding our technological infrastructure and, ultimately, our future in space. As we continue to explore and expand our presence in the cosmos, understanding and protecting against space weather phenomena will be more important than ever. The Van Allen radiation belts are regions of intense radiation trapped within Earth's magnetic field. These belts consist of high-energy charged particles, primarily protons and electrons, originating from the sun and cosmic rays. They form two distinct zones, the inner and outer belts, each with unique characteristics and composition. The belts play a crucial role in protecting life on Earth by acting as a shield against harmful radiation. They deflect and trap high-energy particles that would otherwise bombard our planet, stripping away our atmosphere and making life impossible. Understanding the Van Allen belts is not just an academic exercise, it has real-world implications for us. As we venture further into space, our spacecraft and astronauts are increasingly exposed to the hazards of radiation. The knowledge gained from studying these belts is crucial for developing effective shielding and ensuring the safety of future space missions. The Van Allen belts serve as a stark reminder of the dangers lurking in the cosmos. They highlight the importance of continued research and exploration to unravel the mysteries of space and ensure the safety of our technological civilization as we venture beyond Earth. The Van Allen belts are not a single uniform entity, but rather a complex system of two distinct zones, the inner and outer belts. These belts are regions of space where charged particles, primarily electrons and protons, are trapped by Earth's magnetic field. They were discovered in 1958 by James Van Allen, an American space scientist, during the early days of space exploration. The belts play a crucial role in protecting our planet from the harmful effects of solar radiation and cosmic rays. The inner belt, closer to Earth, is a region of intense radiation, primarily composed of high-energy protons. These protons are highly energetic and can pose significant risks to both astronauts and satellites. The inner belt is relatively stable and its intensity does not fluctuate as much as the outer belt. This stability is due to the fact that the inner belt is shielded from the direct influence of solar activity by the Earth's magnetic field. It extends from about 600 miles to 3,700 miles above Earth's surface. This region is densely packed with high-energy protons, which are remnants of cosmic rays that have collided with the Earth's atmosphere. The inner belt's radiation levels are so intense that they can damage the electronic components of satellites and pose health risks to astronauts if not properly shielded. The outer belt, located further out, is dominated by high-energy electrons and is much larger and more dynamic than the inner belt. Unlike the inner belt, the outer belt's intensity can vary greatly due to solar activity. During periods of high solar activity, the outer belt can swell and become more intense, posing additional risks to satellites and spacecraft. It stretches from approximately 8,400 miles to 36,000 miles above Earth. This vast region is filled with high-energy electrons that can penetrate the outer layers of spacecraft and cause significant damage to their electronic systems. The outer belt is also more susceptible to changes in space weather, which can lead to sudden increases in radiation levels. The composition and intensity of both belts can fluctuate dramatically, influenced by solar activity and space weather. Solar storms, for example, can inject large amounts of energy into the belts, causing them to expand and intensify. This can lead to increased radiation levels that can affect satellites, spacecraft, and even power grids on Earth. The distinct characteristics of the inner and outer belts arise from the different sources and energies of the trapped particles. The inner belt's protons are primarily the result of cosmic ray interactions, while the outer belt's electrons are mainly from the solar wind. This difference in particle sources leads to the unique behaviors and properties of each belt. The inner belt's protons originate mainly from cosmic ray interactions with Earth's atmosphere. When cosmic rays, which are high-energy particles from outer space, collide with the Earth's atmosphere, they produce secondary particles, including protons, that become trapped in the inner belt. This process creates a dense region of high-energy protons that can pose significant risks to space missions. In contrast, the outer belt's electrons are primarily from the solar wind, a stream of charged particles constantly emanating from the sun. These electrons are captured by the Earth's magnetic field and become trapped in the outer belt. The solar wind's variability means that the outer belt's intensity can change rapidly, especially during solar storms. Understanding the structure and composition of these belts is crucial for mitigating the risks they pose to satellites and spacecraft. Engineers must design satellites with adequate shielding to protect against the intense radiation in the belts. Additionally, mission planners must carefully consider the timing and trajectory of space missions to minimize exposure to the most hazardous regions of the belts. Different regions of the belts present varying levels of radiation hazard, requiring careful mission planning and spacecraft design to ensure their protection. By understanding the dynamics of the Van Allen belts, scientists and engineers can develop strategies to safeguard our technology and astronauts, ensuring the continued success of space exploration. The existence of the Van Allen belts is a testament to the power of Earth's magnetic field. These belts are named after Dr. James Van Allen, who discovered them in 1958 using data from the Explorer 1 and Explorer 3 missions. His groundbreaking work revealed the presence of these radiation belts, which are now known to play a crucial role in protecting our planet from harmful solar and cosmic radiation. This invisible force field acts as a giant magnetic dipole, with north and south poles extending thousands of miles into space. The magnetic field is generated by the movement of molten iron and nickel in Earth's outer core, creating electric currents that produce the magnetic field. This field is not static, it fluctuates and changes over time due to various factors including solar activity and the dynamics of Earth's interior. It is this magnetic field that traps charged particles from the sun and cosmic rays, forming the radiation belts. These particles, primarily electrons and protons, are captured and held in place by the magnetic field, creating two distinct regions of trapped radiation, the inner and outer Van Allen belts. The inner belt is dominated by high-energy protons, while the outer belt contains a mix of protons and electrons. The process of trapping these particles is a complex dance between the Earth's magnetic field and the particles' motion. As these charged particles move through space, they interact with the magnetic field, experiencing forces that alter their trajectories. This interaction is governed by the principles of electromagnetism, which dictate how charged particles behave in the presence of a magnetic field. As charged particles from the Sun, carried by the solar wind, approach Earth, they encounter the magnetic field. The solar wind is a stream of charged particles released from the upper atmosphere of the Sun, known as the corona. When these particles reach Earth, they are deflected by the magnetic field, preventing them from directly impacting the planet's surface. The field exerts a force on the particles, causing them to spiral along the magnetic field lines. This spiraling motion is a result of the Lorentz force, which acts perpendicular to both the magnetic field and the velocity of the particles. As a result, the particles follow helical paths along the magnetic field lines, moving back and forth between the poles. These particles are then funneled towards Earth's poles, where the magnetic field lines converge. The convergence of the field lines at the poles creates regions of intense magnetic activity, known as the polar cusps. Here, the particles are guided along the field lines, moving closer to the Earth's surface. As they approach the poles, the particles encounter a stronger magnetic field, which reflects them back towards the equator. This reflection occurs because the magnetic field strength increases near the poles, creating a magnetic mirror effect. The particles are unable to penetrate this stronger field and are instead bounced back along the field lines. This process of bouncing back and forth between the poles traps the particles within the Earth's magnetic field, forming the Van Allen belts. The trapped particles oscillate between the northern and southern hemispheres, creating a dynamic and ever-changing radiation environment. These belts are not uniform. Their shape and intensity can vary depending on solar activity and other factors. The efficiency of this trapping mechanism and consequently the intensity of the radiation belts depend on the strength and orientation of the Earth's magnetic field, which can fluctuate over time. These fluctuations can be caused by geomagnetic storms, which are temporary disturbances in the Earth's magnetosphere caused by solar wind and solar flares. During such events, the radiation belts can become more intense and expand, posing a greater risk to satellites and astronauts. Understanding these dynamics is crucial for predicting the belt's behavior and their potential impact on spacecraft and astronauts. By studying the Van Allen belts, scientists can develop better strategies to protect our technology and human explorers from the harmful effects of radiation. This knowledge is essential for the future of space exploration, as we venture further into the cosmos and encounter new and challenging environments.